Traveling waves. Okay. So we talked about simple harmonic motion. We talked about disturbances last week. Again, this is stuff you've learned in physical science. It's just a little bit of review. It's been a while, I know, for some of us, but a lot of this stuff is pretty straightforward. Okay? So the basic definition of a wave that everyone said last week when we started this was that wave is a transfer of energy. Okay? So a transfer of energy that basically is caused through a disturbance, right? From my wonderful drawings here, okay? This is a drum, yes? And a drum can create a sound wave by doing what to it? By hitting it and causing the surface of the drum to vibrate, yes? That disturbance creates sound, which transfers energy through the air to us. Our ear then picks up that vibration of sound, right? And that's how we basically cause neurons to fire to our brain saying, hey, we hear something, okay? If the drum isn't hit, there's no sound. If there's no air in the room, if we're in a vacuum and magically alive, yes, there's still no sound because there's nothing for that wave to travel through. Sound is a mechanical wave. We'll go through all of this today. But sound is a mechanical wave, all right? The other one is a slinky or a snaky. Okay.
Calls it a snaky.
And you guys have seen demonstrations with waves on a slinky or a snaky.
Stop calling it that.
Hey guys, there's probably a reason I'm saying that.
Oh,
okay. No, it's not because it slithers.
I don't know.
It's weird.
Where's the snake? Mr. Ellis is losing everything. Losing his mind, losing his snake football club.
All right. But if we have a slinky stretched out, right, it's just going to be a straight line, yes? Once we hit it, right, and we disturb it, then we can create a wave that looks like this. You guys know what I'm talking about? Okay, and it's going to travel down, okay? So here's what's true about traveling waves. The energy is the thing that moves. The particles that the wave is traveling through oscillate, but then they return to equilibrium, okay? So this slinky, when this wave is traveling through it, this slinky will move up and down, but then it will return to its original position. Everybody agree with that? Okay, so it's the energy that moves through the particles, not the particles that move from one place to another. All right, mechanical versus electromagnetic waves. All right, you've learned this before. Just a review. Mechanical is something that requires a medium to move. All right, it requires a medium to move. A medium is just what a wave moves through. Okay, so our sound waves right now are moving through the medium of air. Can they move through liquids? Yes. Can they move through solids? Yes. Right? It's just dependent upon the medium. Okay, and we'll talk about that. Right? Mechanical waves require a medium to move through. Examples, sound, slinkies, waters. Almost every wave you consider a wave, right, is a mechanical wave. The only ones that are not mechanical waves are electromagnetic waves, which they can travel through mediums, but they don't need one, right? So they can travel through a vacuum or just an absence of materials, okay? Electromagnetic waves, basically lights or anything on the electromagnetic spectrum. We will go into the electromagnetic spectrum more detail here in just a little bit. So if you don't want to copy all these down, don't do it now because we'll focus on it at the very end. Cool with that?
Gravitational waves.
Okay. Not something that we're going to focus on. Okay.
So no quantum field.
Not right now. No. I don't even know where to fit this. Okay. Main thing we got to understand, mechanicals require a medium or something for the wave to travel through. Electromagnetic can travel through a medium, but it doesn't have to. Everybody good with that? The speed of a wave depends on the medium it travels through, but we can calculate this speed of a wave using this equation. And this is the equation that's written in your reference booklet. Okay, C stands for speed of a wave. F stands for frequency, and wavelength stands for lambda. Have we shown lambda yet? Okay, so it's lambda. It's like kind of drawing like a little dinosaur. I mean, I don't really know how to describe it, just besides you draw like a script F is like this. Lambda is like a backwards script F, and give it a front leg. Okay, so that's how you draw lambda. That's wavelength. And here's why this makes sense unit-wise. Okay. Frequency is measured in hertz, which is 1/seconds. Okay. Or as IB likes to write it, seconds to the -1. Same thing. Okay. Wavelength, and this is actually really good just to understand. Wavelength is measured in meters. Yes? Everybody cool with that? So when we multiply frequency times wavelength, we multiply, let me write it frequency first, seconds to the -1 times meters, which we can then write as meters seconds to the -1. Yes? Which is written as meters per seconds. There. Yes? So does everybody see how these two concepts can go together to make a speed in meters per second? Fair enough? Okay. Another way to remember this is frequency is 1/period. Yes? Frequency is 1/period. And what does period tell me? It's the seconds for what? 1 lambda. Yes? So if I were to do, we can also write this as speed equals wavelength divided by period. Yes? Distance, seconds for 1 wavelength. Okay? So again, this is still meters over seconds. Everybody get that with that? Say that again. All right. Almost done. I think we have 2 more slides and then we're done. Okay. Sound. So sound is a mechanical wave. All right. It's a special mechanical wave. Sound is a special mechanical wave that we like to focus on. Okay. It is a compression wave. Basically, every concept of a wave applies to sound. We need to understand, though, that frequency applies to pitch or notes. Right? If you're in music, you probably understand this already. Right? Right? Thank you. Low frequency, I don't vibrate my lips very fast. Right? I vibrate them at a faster frequency. I get a higher pitch. Okay? There you go. Amplitude deals with the volume, how loud it is, right? Can I have a low amplitude, high frequency sound? Yes. All right? Use these terms. Instead of saying pitch or notes or volume, you say amplitude or frequency. Can we handle that? Okay. Also, it has this in there like, this is a great thing for students to know. The great way to measure the speed of sound is to have an echo. Okay. If you were to clap, that sound wave goes and hits a solid object and then bounces back and you hear that echo. Yes? I could then do speed as distance divided by time, but I need to know that my distance is twice the length from where I stand to the solid object, because it has to travel there and then it has to travel back. Good. All right. Let's just.
Mr. Ellis, man.
Oh, you guys hear that one?
Yeah.
I can't hear that. That's beautiful. Yeah, I can't hear that. All right. I was thinking we'd be. Okay, I can. Oh, that's not bad.
That's not as painful.
Okay, I can hear that one.
I should do this in my math class because the just don't like to hear it.
Hey, guess what?
No one else be going crazy.
You'll be there at one point in your life, right? Okay. Just if you want to see what your future looks like, just go home, look at your mom and dad, and just say, "This is me in 30 years." Like, I just have to accept that. This is my life. This is what I'm going to look like. This is my attitude. My dress is going to look just like this in 30 years. Like, you can try to deny it as much as you want right now, but it's just true. Okay. And your hearing will be equally as bad. All right. So that's 8,000 kilohertz. Okay. Or 8 kilohertz, excuse me. So 8. I'll tell you. Okay. It's okay. I'll tell you. Everyone should be able to hear this 8,000 times per second. Your eardrum is vibrating. Yes? Okay. You hear that? That's 10 kilohertz. Okay. So our frequency just went up, meaning our wavelength went shorter. Yes? Okay. I can hear that.
Is there a reason that like high pitched noises make my eyes water?
That's 12? I don't know. Ask
do
Mr.
you
Rabel
Because you're connected to
or Mr. McKenzie. Yeah, I can hear that. So 12 kilohertz is about, it says basically 50 and younger can hear. Okay, so this is 14. Ooh, I can barely hear that. Yeah, I can barely hear that. So that's 45 and younger. I can hear this barely. It doesn't hurt. That's 15 kilohertz. That's 39 and younger. I can't hear this. That's 16 kilohertz, right? And that's 30 and younger, which, you know, I'm older than 30. So.
Let's see who's the best.
All right. All right, close your eyes. Raise your hand when you can hear the sound that I play. Everyone should have been able to hear that. It's 24 and younger. Okay, just played one. That was 18. That was 18. That's 19. That's 20. Yeah, so 20 and younger, you guys are 22 and younger.
Yeah. I could hear. So I think
Now, and then this one it says only dogs can hear. I'm just joking. You guys are all dogs. All right. Well, you want to just keep going?
I can hear that.
Okay. Focus Physics Tuesday. Electromagnetic waves. It is, yeah, until the 28th. And then after that, it's just party. Yep. Okay. 3 electromagnetic waves. These are waves that can travel through a medium, but they do not require one. Yes? Okay. The acronym, is it an acronym? Yeah. That I teach freshmen, that I was taught by other people, is rich men invent very unique Xbox. Okay? You don't want to do it? That's fine. Come up with one of your own. But Richmond invent very unique Xbox games: radio, micro, infrared, near infrared, visible, ultraviolet, X-ray, and gamma. All of these are electromagnetic waves. All of these travel at the speed of light. They are all lights. They are just different forms of light. Okay? We see a very small spectrum of this. All right? I don't know why, but IB wants you to memorize what's in the blue. Okay? I don't know. It just is. I do what I'm told. I know you guys don't all do that, but I try to do what I'm told. Like they say, it says you should have a good idea as to like what the range of wavelengths are for all of these. So I'm sorry. I would never make someone do that. Never. This is the second year you've had me, Ellie. Do you feel like I would?
Isn't like near infrared like what they use for night vision and far infrared what they use for like thermal cameras?
I believe so. I could be wrong. I don't know. Electromagnetic waves. Radio, highest wavelength or longest is probably the better way to describe that. Longest wavelength, lowest frequency, lowest energy. Anything to the left of this on the visible spectrum is not dangerous to you. Okay? Anything to the right is dangerous to you. That's why we protect ourselves from ultraviolet rays. That's why we try not to use too many X-rays, or we put lead on top of us to protect us from X-rays when we have to get one. And that's why we try to stay away from radioactive places that have gamma, like Chernobyl, right? Okay? So, guys, just notice with this, okay? As the wavelength gets shorter, the frequency gets higher. Yeah, near. And the energy gets higher. So gamma has the highest energy, X-ray, ultraviolet. Visible then, it should make sense, guys. This is infrared, and the red is closest to that on the visible spectrum. Ultraviolet is just past violet, okay? So red has the lowest frequency and the highest wavelength. Purple has the highest frequency and the shortest wavelength, okay? This is why red is often used for night vision or in photography studios, okay? Because photography uses energy to develop paper. And if we just have a red light in there, we have very low light, low energy light. That's not going to expose the film, okay? Whereas purple light would expose it, right? Same idea for night vision, right? If you have a headlamp that has like a red light on it, or you've seen red light for night vision, your eyes dilate. They get bigger and smaller based on the intensity of light, okay? They get smaller when there's too much energy, right? When you go out in the sun, your pupils get smaller because they don't want to let so much energy in because it can hurt them, okay? When it's dark, your eyes get bigger, and that allows you to see better at night to allow really low amounts of light in, right? Well, if you have a headlamp that has a white light, you just exposed yourself to all this bright light, and so your pupils are going to dilate, or no, not dilate, the opposite of dilate, yes? And it will then be hard to see once that light goes away. But if you have a red light, it's low energy, so your pupils don't get smaller, so you still have the ability to see in low light situations. It's also why if you're sleeping, a red light will not wake you up, whereas a blue light or purple light will always wake you up. It's because your body senses that high energy, and it will cause you to wake up. So if you have like my kid has a multicolored nightlight, and we only ever put it on red. Because if we put it on other colors, they will naturally wake up. Or if you have one that like rotates colors, when it's blue, they will wake up because their body senses that high energy. What?
What's dangerous? Low frequency? Is the low wave
High frequency is dangerous. Ultraviolets, think of things we protect ourselves from. Ultraviolet, X-rays, and gammas, right? It's okay having the radio on. Radio waves are traveling all around us and through us right now. They're low energy. They don't hurt us. Microwaves, you can stand in front of the microwave. Even though grandma says not to, you'll probably be okay, okay? Infrared, not a big deal. Visible light, obviously we can see. We protect ourselves from this, and this. Yes? Okay. We put a lotion on us, which absorbs ultraviolet light to protect us from this. We put lead on us, and we bury things in concrete to protect us from this. Okay? Fair enough? That's fine. Hey, you don't write it down. Your choice. Electromagnetic waves are transverse waves, right? The terms we need to understand is frequency determines the color or the type of wave. Amplitude determines the brightness, right? It is an electromagnetic wave. It's a really hard thing to draw down here, but basically the red is like an electric field which oscillates back and forth. The B is a magnetic field that oscillates back and forth, okay? That is an electromagnetic wave. And I'm going to prove to you that light is an electromagnetic wave here, and then we'll be done for the day. Sound good?
So you can use light to generate a magnetic field.
Oh, like an anthill that's getting built over here on this table.
Yeah, because remember magnetic.
Ew.
It's okay.
I don't like
You'll be
ants.
all right.
They scare me.
Why?
They're creepy looking.
I was trying 7 years old the road when I was really little. And it was on my snow. And I literally.
Yeah, remember magnetic
field
field perpendicular 90 degrees cosine.
Not. No, you're mixed.
I was looking.
Oh, these are sunglasses? Do we get free sunglasses?
How was that?
Yeah, free sunglasses. You know, I sold that on the single marketplace for $20.
Look, guys.
You guys, sure.
I was I looked for one for to get one from you.